Alright, so the last topic on our test is the most recent topic that we've talked about, and that is conservation of energy. Basic ideas about energy. Energy is the ability of an object to change itself or the world around it. Okay, we're now going to go through the different types of energy and when we have them. Kinetic energy, exists whenever an object is moving, given by 1/2 mv squared. Gravitational potential energy happens whenever an object has height, and we find it with UG equals mgh. And spring potential energy occurs whenever we have a spring being stretched or compressed, as US equals 1/2 kx squared. Okay, moving on to work. Okay, work is defined as the change in energy, from a force. Right. We've seen that forces, whether it's friction, pushes, pulls, etc., can change the energy of an object. In fact, that's one of the ways that objects transfer energy between themselves is through that force. So when we have a force being exerted on an object over a distance, it can lead to a change in energy, and we call this work. We have three ways to find work. The first is work is simply the change in energy. Okay, that's really going back to the true meaning of it. Keep in mind that a change in energy is going to be final minus initial. We also can find it based off of the force and the displacement over which that force is exerted. That's our F delta x cosine theta, and we remember that theta is the angle between the force and the distance. Okay, when we're thinking about this, we don't have to worry about the sign of our force, the sign of our displacement. We simply can use the magnitude of both and then correctly identify that angle, the angle between the force and the displacement, and that's what that theta is. And the last way we can find the work is if we have a graph of force versus position or displacement, and we find the area. So the area under the curve on that graph, which could be negative, by the way, if it's below the axis, that is also the work. Lastly, we talked briefly about heat, at least a simplified version of heat, and we said for now that heat is the work done or the energy lost due to friction, air resistance, etc. Okay, so when friction or air resistance or other forces like that cause an object to lose energy, that energy becomes heat. Okay, and we can talk a lot more about that later, but right now that's what we're going to use for our definition of heat. Alright, so moving on to the big idea with energy, and that is conservation of energy. And the basic concept of this is that the total energy of the universe is constant. Alright, so when something is conserved, it means it doesn't change. So in this case, the total energy of the universe is conserved, it doesn't change. Individual objects, however, can change their energies, and this occurs in two ways. The first is if the energy changes forms. Okay, so this would be kinetic becoming potential, or some other example. So we might have an object moving and then it travels up a hill. Its kinetic energy is becoming potential energy. When that happens, though, those changes in forms, we have no change in the total energy, and we saw that in our lab. We've seen that in many problems. Okay, the total energy does not change when the energy simply changes forms. The other change we can have is when work is done by a non-conservative force. Alright, and we'll talk in a second about what that means, but in these cases, there is a change to the total energy. Our basic formula for solving these is E initial plus work and C equals E final. So the thing we really want to think about is setting up that equation. So we're thinking about what kind of energy the object starts with, is there any work being done, and what kind of energy the object ends with. Something else we want to keep in mind is this meaning of non-conservative, right? We talk about non-conservative forces, and the most basic way I think about this is that work done by a non-conservative force can't be undone. So friction, pushes, pulls, things like that, those are all non-conservative forces. Fg and FF, or Fs, are conservative, okay? We can undo the work done by them. And for that reason, okay, we're going to use UG and US, the spring potential energy and gravitational potential energy, when we're dealing with those forces and the changes in energy for those forces. We don't say that gravity does work, although it does. We usually think instead about energy being stored as gravitational potential energy. And the last little thing we had is power. And power is a measure of the rate of energy usage, okay? How quickly energy is used. And the way we find it, very simply, is that the average power is the work done over the time. Keep in mind there are a few ways of finding work, but that's what average power would be. We didn't deal with non-average power, so we don't have to worry about how we would find that. Okay, so we're going to begin our review here, first talking about momentum. So the basic definition of momentum is really a measure of an object's motion, or who would win in a collision is how I always think about it. And the equation is given by P, the momentum, is equal to mass times velocity. Now our next quantity, impulse. Impulse is actually just the change in the momentum. Okay, and that by itself isn't useful, but the way we can use impulse is because we can link impulse to force, as you'll see in a second. Conceptually, impulse tells us that by extending the time of a collision, we can decrease the force. So if we have a given collision, a longer collision is going to result in less force, and a shorter collision is going to result in more force. All right, so there's that inverse relationship between the force and the time. We had three ways that we used to calculate impulse. Okay, the first was going back basically to the definition of impulse. If the momentum is changing, and that's what impulse is, it's the change in momentum, then it's probably going to be the velocity that's changing. So one way to calculate the impulse, the change in momentum, is mass times change in velocity. Another way is average force times change in time, and this links back to that conceptual idea that we were just talking about. And the third is the area on a force versus time graph, okay? That is also the impulse. A few problem-solving tips with impulse. We want to be careful of our signs, especially when we're looking at the sign of velocity and the sign of force. If they're in opposite directions, we need to indicate that with a negative. Another thing to keep in mind here with impulse is the change in velocity is going to be v final minus v initial, as with any change. And the last thing is really just to remember that we have three ways of finding that change in momentum. So we really just want to find delta P using one of those methods, and then we can go from there, and we can use that impulse to find something else. All right, moving on here to conservation of momentum, the other thing we did with momentum. The first thing is knowing when momentum is useful. So momentum is going to be useful when we're analyzing collisions or explosions between two or more objects. All right, that's when momentum is really most useful, or conservation of momentum. And the basic idea is that in any collision or explosion, okay, the total momentum of the system is conserved, okay? So it doesn't change, the total for all the objects in our system. Now, there is one really, really important caveat here, okay? Assuming no outside net forces, okay? So if we have, say, friction acting on our objects, all right, that would be an outside net force. That would cause the momentum to not be conserved. If they're going up or down a hill, then gravity would be an outside net force causing momentum to not be conserved. So there are a few situations where momentum won't be conserved. But if the only forces that exist, the only net forces that exist, are between the objects, resulting from the collisions themselves, okay, then momentum is going to be conserved. All right, our formula for conservation of momentum is pretty basic here. It's just that momentum initial equals momentum final. All right, so really nothing to it. It's more in the application of it. So the way we're going to solve these, okay, we're going to start by setting up that equation, that conservation of momentum. Momentum initial equals momentum final. Two things related to that I think help setting it up is first is drawing a picture. Okay, I think that makes it easier. The second is we're going to consider this question: what has momentum in our system, both before and after the collision or explosion or whatever is happening here? Okay, so what objects have momentum, which is really another way of saying what objects are moving. Some other things to keep in mind, okay, we want to be careful with signs. That's a big one, okay. Having a momentum of 0 is okay. There's nothing wrong with having a momentum of 0. That will happen sometimes. And if they stick together, okay, we've seen this a few times, the trick is we're going to add the masses. We're going to treat them as a single object. One last thing, we already talked about this some, but keep in mind, yet again, momentum is only conserved when there are no outside forces. So, sometimes we may look at conservation of momentum for part of a problem, okay, look at one segment or one piece of a problem where momentum is conserved. But then we might need to employ some other ideas, energy, forces, kinematics, etc. So keep in mind that only for that period of time when there's no outside forces can we use conservation of momentum. All right, two other side things kind of related to conservation of momentum that we talked about were two-dimensional momentum, and what really happens there is the same thing that happened with forces in 2 dimensions. We simply have momentum being conserved in both the x and y directions. Okay, so we have momentum initial in the x equals momentum final in the x, and momentum initial in the y equals momentum final in the y. Okay, so some basic tips here. Like we've done with force problems, we're just going to separate the problem into two, separate it into x and y components, and we're going to set up conservation of momentum in both directions, both the x and the y. And then if we need to, at the end, we're going to recombine and put it back together using Pythagorean theorem and using trig. All right, two other important ideas here. The difference between an elastic and an inelastic collision. So inelastic collision means energy is not conserved. Okay, but momentum still is, assuming no outside forces. Just as a quick side note here, if they stick together, okay, the case when they stick together, this would qualify as an inelastic collision. Whenever they stick together, energy is going to be lost in the collision, but momentum, assuming no outside forces, is still conserved. An elastic collision simply means that energy is conserved in addition to momentum. Okay, so both energy and momentum are conserved if our collision is elastic. Okay, so moving on to rotational motion, the first thing we talked about with rotational was rotational kinematics, right? And what we discovered was that the equations are exactly the same, all right? We just have new variables here. So those are your 4 new kinematics equations, and what you're seeing is delta x is becoming delta theta, velocity is becoming omega, and acceleration is becoming alpha. For rotational, we had 2 directions. Instead of up, down, left, right, we care about clockwise and counterclockwise. The standard is that clockwise is negative, counterclockwise is positive. However, you obviously can use whatever convention you would like as long as you are consistent. In addition, we talked about a few situations where we're going to have both linear and angular quantities here, and we have a way of converting between the two. So, in every case, if we want to go from the angular quantity to the linear, we simply multiply by the radius. And there are two situations where this comes into play. The first is if an object is rolling smoothly along the ground, then we want to link the velocity of its center of mass to the angular velocity of the object rolling. Okay, so this is rolling smoothly is the key here. And the other situation that we're going to talk about is linking a rotating object. All right, so an object is rotating in place. All right, to the velocity, the tangential velocity of a point on that object. And in both cases, we consider these linear velocities, but technically this is usually referred to as translational velocity or translational acceleration. So the velocity or acceleration of the object as a whole relative to its rotational quantities. And in this case, when we're thinking about a point on a rotating object, we're calling that our tangential. Like I said, both are linear quantities, but one we call translational, one we call tangential. You do not necessarily need to know those terms though. All right, a few tips for solving these problems. We're solving them in a very similar way to what we did with regular kinematics. So the first thing is to set up our chart. So that would be our chart with our 5 variables, okay? So we're always going to do it for rotational. We may need to set up linear too, okay, if needed, if we have both linear and rotational quantities. We also want to consider our connections, consider our links between the two that we just talked about. And lastly, as always, we want to be careful with our signs here. Okay, be consistent with our clockwise, counterclockwise, and same thing if we have linear quantities, thinking about up, down, left, right. All right, the other thing we talked about, similar to rotational kinematics, was rotational motion graphs. And just like the link between linear and rotational kinematics, the same link exists between linear motion graphs and rotational motion graphs. So those relationships are the same. On an angular position versus time graph, the angular velocity is the slope, all right, and the angular acceleration is the curvature. All right, it works exactly the same way, as does speeding up, slowing down, all those things that we talked about in the beginning of the year. On an angular velocity versus time graph, the angular displacement is the area, okay, and the angular acceleration on an angular velocity versus time graph is the slope. All right, moving on to torque, all right, which is the rotational equivalent of force. So the definition, we've said before, it's an off-center force that causes rotation. Another way of thinking about it is it's simply rotational force. It is the rotational version of the force. And the way we're going to find it is that torque is equal to RF sine of theta, keeping in mind that R is that distance from the pivot. All right. So that's going to be an important piece. We now care not only about what force we have, but where that force acts. Some other things to keep in mind. Theta is the angle between R and F. Another important piece here is that a force acting on the pivot leads to no torque. All right, so we have to have a force away from our pivot in order to create a torque. Next thing up was in our rotational unit was the moment of inertia. And the easiest way to describe that is it's simply the rotational version of mass. Another way of thinking about it is it describes how difficult it is to rotate an object. All right, so what things affect the moment of inertia? Well, the mass absolutely does, as does size and shape of the object. Okay, but the real key, the thing that really matters is the distribution of the mass relative to the axis of rotation. So the more mass we have further away from this, the greater the moment of inertia. The one other thing, and you're not going to be doing a ton calculating moment of inertias as you've seen. You will be given the formula if you need to calculate it. But the other important thing to remember is if you have multiple objects, okay, we want to calculate the moment of inertia of each and add them. All right, so bringing all this together, Newton's laws for rotation. They are exactly the same as Newton's laws for just regular motion, except instead of forces, we're talking about torques, and instead of mass, we're talking about moment of inertia. So the first law, just like the first law for regular motion, tells us that unbalanced torques are needed in order to cause an angular acceleration, and if there are none, we'll have a constant angular velocity. The second is that the sum of the torques is equal to I alpha, just like force is equal to mass times acceleration. And the third is the idea of equal and opposite torques, okay? And that one probably doesn't come into play quite as much as it did with equal and opposite forces. But we did see it on something like the beetle walking on the record. The beetle exerted and the record exerted equal and opposite torques on each other. When you're solving these, the first thing we always want to do, just like with regular force problems, is draw a picture. The new thing to consider here is where do those forces act? Okay, that's something that we haven't considered before. Second, we want to set up F equals ma as well if we need it, okay? If there is an object that's undergoing a linear acceleration, then we want to set up our F equals ma too. Another thing that's really important are signs, as always, okay? And knowing this relationship, that A is equal to R alpha. As you may remember, that's a substitution we made a lot for these problems. All right, moving on to equilibrium, which is really an application of torques. Equilibrium simply occurs when our acceleration is 0 and our angular acceleration is 0. So that means that the sum of our forces acting on an object, and it's usually a beam or some long object that's balancing. Okay, so some of the forces acting on that object is going to be 0, and the sum of the torques is also going to be 0. So the first thing we want to do is we want to identify all the forces when we're solving these problems and where they act. Okay, that once again is really important. We're then going to pick a pivot, okay, which could be anything. All right, you could pick any point to be a pivot, and you have to have the sum of the torques add up to 0 about that point. And then lastly, we're going to start with the sum of the torques is equal to 0. You may need to also bring in this sum of the forces is equal to 0, but sum of the torques equals 0 is going to be the most useful way to start. All right, a few other tips here. The first is picking a good pivot point. We said we can pick anything to be a pivot point, but there are some things that make a good pivot point. So the key is to pick a pivot where there's an unknown force and one that we don't care about, because then the force or the torque from that force is 0 since it acts on the pivot. Another thing to keep in mind is that gravity on uniform objects acts in the center of the object. And lastly, remember, we can also use forces, and we can use forces in both the x and the y directions. So we can say the sum of the forces in the x is 0, and the sum of the forces in the y is 0. Last thing to keep in mind, this is just a nice little trick to have in your back pocket here, is the link between equilibrium and center of mass. The trick is that a group of objects will balance at the center of mass. So we remember that that equation is x1m1 plus x2m2 and so on. All right. So if we're simply looking for where the object is going to balance, okay, where we should place a fulcrum or something else to balance it, finding the center of mass can do that. All right, moving on here to rotational kinetic energy, which was our next idea. And that is, the basic idea here is that any object that's rotating is going to have a different form of kinetic energy, rotational kinetic energy. Additionally, if an object's rolling, the object as a whole is moving, and the object is rotating. So that means it's going to have both types of kinetic energy, both linear and rotational. So the way we're going to calculate this is that rotational kinetic energy is 1/2 I omega squared, okay? And the work done by a torque, all right, much like work done by a force was F delta x, the work done by a torque is that torque times delta theta, the angular displacement. So when we're solving these, the first thing we're going to want to do is set up conservation of energy, as we always do with any energy. E initial plus work equals E final. The only thing that changes now is we have a new type of energy to consider in these problems. The other thing that's really important is the meaning of this phrasing, rolling smoothly, in these problems. So that means a few things. So the first thing that it means is that we have no work done by the force of friction. Okay, any work done from friction becomes rotational kinetic energy. So there's no work, no energy lost. All right, and the other thing is in these problems, we can use that substitution, that link between angular and rotational, that V equals R omega. All right, so moving on here, we're going to start talking about angular momentum. So, at its most basic level, it's simply the angular version of momentum. We symbolize it with the letter L, and its basic formula is moment of inertia, I times angular speed. Right? And all the other equations that we looked at with regular momentum still apply. So we can say that angular momentum is conserved. We also can say that a change in angular momentum is going to be equal to a torque rather than a force exerted over a period of time. So first of all, we're going to use this angular momentum for situations where there's an angular collision, okay? And I put that in quotes because it's sometimes a little bit different than a normal collision that we think of, but two objects rotating independently and then rotating together, or vice versa. Or situations where we have a single object and the moment of inertia, I, changes. Okay, that's another use for conservation of angular momentum. So we're going to set up Li equals Lf like we would for any other or just a regular momentum problem. Now there is that one little trick we use when it's just the moment of inertia that changes, and we'll talk about that in a second. The other thing to consider is that we can have a linear angular momentum. I know that sounds a little bit weird, but if we pick a pivot, all right, we can have an object that's just moving in a straight line have angular momentum. And we actually have a little shortcut. Now, we didn't talk a ton about this equation, but we do have a little shortcut for being able to find the angular momentum for an object with regular momentum p. And that is, we just do r times our regular momentum. The other thing we can do, all right, is treat it as a point mass with a moment of inertia of mr squared, and it ends up actually working out the exact same way. The last thing, I told you we were going to come back to this, is when can we use that little trick, that I initial omega initial equals I final omega final. So that equation is going to come into play when we have a single object rotating and there's simply a changing moment of inertia. Okay, so this is the figure skater with her arms out and then she brings her arms in. Okay, this explains it conceptually, but we can also use it in an actual situation when that happens.